clearly down in college was a little generous with the wine. We're missing somewhere between 5 or 10 people. But it's a great pleasure to introduce Antonin Chambolle as the first speaker today, and he will be talking about acceleration of primal-dual algorithms, deterministic versus stochastic. Please.
Thank you very much. So, thank you, Anders, for this invitation to this workshop. So, maybe it's okay if the people who drank a bit too much are not here, because it will be slightly technical sometimes. So, I think. So I will describe a recent work with Matthias Erhardt, who is here, and Peter Richter and Karel Schoenlieb on primal-dual algorithm, and on the fact that you can write a stochastic algorithm with essentially the same structure as this deterministic, and find very similar results and acceleration properties in smooth cases. So I will very briefly review. So I think it's about 45 minutes. I have 15.
Yeah. Yeah.
Okay. So I will briefly review in very, very elementary slides how you try to prove acceleration for primal-dual methods. Then I will introduce our class of stochastic algorithm and show how in that particular case the proof for acceleration in the stochastic case is essentially the same as in the deterministic case, and how by tuning properly the probability, so it will be a kind of block descent somehow. So how to tuning the probability of each variable, you can get, as is well known with other algorithms. I mean, it's something which has been observed quite a lot in the past 5-10 years, that you can really get very good convergence rate for smooth objectives, which are even better than usually with deterministic methods. And I will show some experiments. Okay, so typically when you have primal-dual methods, you have a method essentially. So it's a way to write descent methods. You can usually write primal-dual methods as a descent on the primal point followed by an ascent of a dual point, but it's well known in convex optimization that writing things differently, you could write this as some kind of other type of iterative scheme like Douglas-Rashford, which are more like descent schemes. So the idea here is that you have two time steps. So steps, time is really fictitious here. And you find new points by doing a descent with one step, followed by an ascent with the other step. And the point here is that usually you have the steps themselves are not bounded, so you can take them quite freely, but you have to take one according to the other, and essentially their product should be fixed or bounded. But you can have sometimes very large dual steps or very large primal steps, which seems to be an advantage, but in fact the big question with this algorithm is how you choose these steps. So I will partially answer that, but it's well known that there is no satisfactory answer in general. So to prove the convergence, what you establish in general is a kind, so I simplified here a lot the situation. You try to prove a similar descent rule. So usually you consider that your primal has a gamma convex part and your dual has a delta convex part. So it's not exactly the primal and dual which are strongly convex. And here when I say strongly convex, I assume that at least one is non-zero, but maybe the other could be zero. And typically you end up with contraction which look like this, plus terms which are in general the source of the difficulty in the proofs, but let's say the main contraction looks like that. And it's very easy to get the optimal rate for that. So first, of course, it's very, very easy if gamma and delta are both positive. I will show that in one slide. But even if only one is positive and not the other, for instance, if gamma, sorry, this would be equal 0. I was sure I would do this mistake. So if only gamma is positive, then what you simply do is that you vary tau and sigma at each step. So you replace tau by tau n, and you write the previous inequality. So here you have tau n, so what I did is I just multiplied by tau n plus 1 and divided by tau n plus 1, and here I did the same for sigma. So it's just a trick. And you write this, you call this delta n, and you call delta n plus 1 the same ratio with n plus 1, which involves that, and you want essentially this big thing to be equal to something times delta n plus 1, and you want something to be larger than 1. And if it's true, if you can find that, then you're happy, because then you get some contraction. And the point here is that since you have this term which is larger than 1, you can hope to do this. But obviously you see that if you do that, then it means that this term which be larger than 1, so this sigma should increase. So it means it will give you very poor information on this part of the error, but you will have a good information on that part on the error. So that's essentially the rule for getting acceleration is a rule which gives you in general acceleration in, for instance, the primal variable, but very poor information on the dual variable. So as I said before, you usually have to keep this product constant, such that 1 over L square was L square is the Lipschitz constant of, in that case, of the linear operator which appears in your problem. Or if then you will choose this, of course, equal to that, so that you get a go-back contraction of delta L plus 1. So these two terms equal. And you want to find the contraction factor theta n between these two things. And if this is constant, then you can simply say that this is like 1 over tau n plus 1, and this is like 1 over tau n, and you solve. So it's very obvious to solve that. So you find that tau n plus 1 should be decreased, tau n should be decreased, sigma n should be increased. So this one will go to 0, this one to plus infinity, and the ratio is simply, in that case, if you do calculation, is simply given by this quantity. It's a two-line calculation. And what is interesting here is that with this rule, then it's very easy to show that tau n behaves like 1 over n, and precisely 1 over gamma n. Just also an estimate of how the sequence behaves. And it's quite insensitive to the initial choice, because if the initial choice is large, you divide by large numbers, so you go very quickly to low numbers, and when you have low numbers, that is like 1 over n. So in this case, you end up with this rule. So you can write 1 over theta n, but it's even simpler if you write it in this way, because then you find straightforwardly that sigma n delta n is decreasing. So you get a bond of this kind. And in particular, if you look only at the part a n, it's like tau n square something. And as I say, you can take this very large. So this term is almost insensitive, except that in general you don't know this value. So this is also a remark which is a bit void. But in practice, you take this quite large. So it's very simple to analyze that and see that tau n is like 1 over n. So that this gives a 1 over n square convergence for this, which is related. So in that case, it's not clear that it's the optimal rate, but it should be. It's related to optimal rates for the situation I'm considering here. And in case both primal and dual have nice properties, then it's even obviously simpler, because what you simply do is to choose tau n sigma so that you get the same contraction rate for both sides. And actually, that's a much more general trick. If you have some objective which is gamma convex with respect to some metric, then you can adapt your steps of your metric so that you globally have all these kind of equalities. So it's obvious that you take essentially the tau like 1 over gamma or something like this. So you take this kind of inequality. And if you have this, in addition, then you can solve this, and you get that tau n sigma behave like that, for instance, and you get above all a contraction factor which is like this. So you get this rule, and this is usually this is very simple proofs of convergence for very simple algorithms, and it's interesting that these very simple proofs give you what is here almost the optimal contraction factor, which depends. So this object here, which is wrong because the square root should be only on delta gamma and not on L, is really for the, I didn't write the initial problem, I will write it soon, is really the condition number, so it's the square root of the condition number of your problem, which appears here. So it's known that for iterative first order method, the best you can do essentially is to contract with some factor which is related to the square root of the condition number. So this is probably one of the simplest approach to this kind of rates here. So now what I will show is that this structure which has been, so we have studied that quite a few years ago now with Thomas Spock on deterministic algorithm, and we found that for stochastic algorithm with Matthias and Peter and Carola, you could really write the same kind of iterations and find the same structure. So why would you like to use a stochastic algorithm? So it's quite obvious. So here, for instance, the kind of problem I'm looking at, which appear in many fields, for instance, imaging here, is problems where you have a sum of objectives and you could have many functions here. And here we look at simpler problem where I have only one other regularizer somehow here. If you look at inverse problem, this could be a regularizer and it could be some kind of data term. And usually, so in statistical learning, for instance, you have many samples here. Or in inverse problem, you would have maybe a matrix here which is very large and very expensive to compute. So you don't want to compute it. You could have both. So typically what stochastic gradient descent do, they don't evaluate completely this term, so they will estimate the gradient by some random technique. So in a very abstract general way, they will compute some approximate gradient and hope that essentially the rule to compute this approximate gradient ensures that the expectation is the gradient and that the variance is as small as possible. So many recent methods aim really at reducing this variance as much as possible. That's a natural approach. And in general, if you do that as said here and just iterate, this will not converge. This is quite easy to see because when you get close to something of the order of the variance, then you will of course oscillate infinitely and you never really converge. So the simplest strategy which is used usually is to decrease the time step in some way, but this is very long. So there are studies on rates and optimal rates you can get with an abstract gradient method like that, for instance by Nemirovsky, Judiski, Lan and Shapiro. We show that you get 1 over square root of k convergence if you have an L-Lipschitz gradient here. And if you have strongly convex function, you get 1 over k. So it's not something people do know in more, if you know some structure. I mean, if you don't know any structure, it's still something reasonable. So if you if you know the structure, for instance, if the structure is like this, you have many improvements which have appeared in the past 10 years or 5 years. So there are this average gradient technique, so stochastic average gradient techniques. This one is with a G, this one is just a gradient descent on the F term, and this term is with the proximal G, so where the G is solved implicitly at each iteration. You have variance with variance reduction methods. Dual coordinate ascent for this problem. When you dualize, which I will more or less do for the primal-dual, then you get a dual which is yi, and you can do stochastic dual coordinate ascent. There are variants here which have all strange names, so you don't really know what they do. But there is maybe an important paper of Nesterov on coordinate descent for studies general. So, and there are a lot of recent papers also on acceleration. And on primal-dual, and in particular, papers by Farcock and Bianchi. So this one is quite abstract and shows convergence of general primal-dual iteration, so it's interesting. And this one have optimal rates, also this one. And there is a paper of Zheng Jiao, which is almost, it's very close to what I will introduce now, which really adapts essentially the primal-dual approach we had introduced with Thomas Spock to the accelerated primal-dual approach we had introduced in the strongly convex case to get good rates. And here what we did is a slight improvement. We have a slightly different algorithm, but for which we can really analyze and optimize the probabilities and everything. So, as I will describe now. Okay. So I will describe the strongly convex case. We also studied the case where only one side is strongly convex, either this side or this side, which gives some kind of 1/k square acceleration, but it's not completely clear, I mean to me at least, maybe to Matthias it's clearer, how to choose well the probabilities in this other case. While in the purely strongly convex case it's very clear and it gives very, very nice formulas. So the general approach is to rewrite this problem as a saddle point. So I just, of course, dualize this part. I write that fi, which is a convex function, is, so I didn't say everything is convex here, is obtained by its convex conjugate as a sup. So now you have increased, of course, the number of variables. You have added a dual variable for each fi term. And what you will essentially do is a kind of coordinate ascent on y and a descent of x alternatively. But of course, the idea of stochastic method is not to do a global coordinate ascent on y, but just do it with respect to some variables. So you can pick a set of variables, or to simplify, I will just consider one variable, because otherwise the formulas become more complicated. And in our case, we estimate this proximity operator at each iteration, so this probably could be insured. So this means that this is interesting only if this prox is very cheap with respect to this evaluation, of course. Okay, so let me describe the method in the deterministic case. I will give some details, not too many, I hope. So in that case, it's exactly the same case, but with only one variable. And what you do, essentially, as I said, you do a descent step in x and an ascent step in y. And in particular here, the main assumption is that the proximity operators of these are easy to compute. So the proximity operators are, I guess, the one not here, but I can. So how did I write it? It's this kind of evaluation. So this, I said that the minimizer is, you can write it like this, and this is called the prox of tau f at x. And if you look at the Fermat rule, the Euler-Lagrange equation for that, it gives you I mean, the natural way to look at this is to say that this is exactly performing one implicit step of gradient descent on your function f. So what you do here is an explicit step of descent on this term, followed by an implicit term of descent on that term. And here you do an explicit term of descent for this term, followed by an implicit term of descent of that term. And the point is that here, I'm not sure yet that I will use xk or xk plus 1 or whatever. So I put y bar and x bar. And for instance, it's well known that if you put something completely explicit with yk and xk, then this will, this will diverge. You can compute the spectrum of the corresponding problem when you don't have g and f, and it's very clear that it has only eigenvalues larger than 1. So you don't want to do something completely explicit here. But of course, it's clear that since you're evaluating one before the other, you can already put, for instance, xk plus 1 here if this is the order in which you evaluate. So you won't anyway do anything purely explicit. It would be stupid. So how do you analyze this? These are the few technical slides in my talk. So here you simply say that, as written here, X is the minimizer, so by definition, of this problem, which is a strongly convex problem, with strong convexity parameter 1 over tau plus the strong convexity parameter of G. So since this is true, then for all X you have this inequality with xk plus 1. And you have, in addition, a convex, a quadratic deviation from the optimum control on this quadratic deviation with your strong convexity parameter, which is this. And this tau gamma is because G is gamma convex. And so you could keep here a generic X to try to get a bound on the primal-dual gap. This is something interesting, but here I will not consider that particular case. And especially in the smooth case, it's not very interesting, because in the smooth case, it's enough to understand how fast you reach your unique minimizer. So it's not very important to have bounds on the gap here. In the non-smooth case, it would be more interesting. So I take directly X equals X star, which is the solution. In that case, I suppose my objective gamma convex, so I have one unique saddle point. And in that case, I put X star here, I get some inequality. Okay, I don't want you to follow exactly the details of the calculation, but what is important is this contraction term, as I said before. And also, additionally, I can get rid of the G here, because it's not very useful if I don't want to bound the energy. And get rid of the G is also very standard, very easy. You just write the optimality conditions. Then it gives you some inequality, because here you have the subgradient of G at the optimal point. So you use that to get rid of this term. And you end up with some inequality where you only have a contraction for this, as I said before. So this was my AN of the previous slides, of the first slides. Of course, you have some bad terms here. You will try to cancel also to get your convergence. In the same way, it's completely symmetrical here, because I have just one variable y. I can write the inequality for y, and I get the same thing with the contraction here and some terms here. And if I sum both, I get, as I introduced in the initial slides, a kind of ratio of the form something over tau plus something over sigma, larger than something over tau, something over sigma, but at the next rank with some contraction. And of course, life is not so simple. I have some cross terms which I want to control, and the only real trick to make this work is to choose properly this y bar and x bar, so that you will be able to control essentially this term with these terms. And if you can do that, then it's over, because then you're really in the situation of the first slides. Okay, so this again is a bit technical. I mean, here in practice, in the smooth case, what you do, as I said before, you can choose one variable, for instance, x as xk plus 1, because xk plus 1 is computed before y, k plus 1. You could also symmetrically choose y bar equals yk plus 1. And then in practice, what we found is that if you take this kind of relaxation for y bar with some theta, which I will determine by the calculation, then this cross term becomes very nice, because so this first term disappears because I have taken x bar equals xk plus 1, so this is cancelled. So here I replace y bar by this, and I get this kind of iteration. So where here I have a difference at step k and a difference at step k minus 1. So and then what I do is that I write this as something at step k plus 1 minus something at step k, and here the only thing I have done is replace this with that. So I just compensate, and you see that this is more or less finished, because here when I will sum my iterations to get a global bound, these terms will cancel if I multiply properly by some theta to the k. And these ones involve only the differences, so they will be easily controlled by this additional thing which was here. So this is very simple. This is the only trick of this of these proofs. So the two first terms will disappear, as I say, in some sum after multiplication. The last term is controlled. So you just say that this is controlled by this quantity, and so it's just saying AB is less than A2 plus B2 over 2. And you choose sigma properly with respect to tau, and you will end up with the control of that. So in the end, it's as my first slide, you take, it's exactly as before, you take this, you have this, so here it's a bit improved with respect to what I wrote before, because you realize by looking at this scheme that you can take tau sigma L square like 1 over theta. And if you introduce the condition number of your problem, so why is this the condition number of your problem? Somehow because you see that, so I have to go back to my initial problem here, f of ax plus g, L square over gamma is essentially the Lipschitz constant of the gradient of this thing, because f star is gamma convex, means that the gradient of this f is 1 over gamma Lipschitz, and with the a you get norm of a square over L over gamma as the Lipschitz constant of the gradient here, and then you have or over delta was the strong convexity, and then this gamma is the strong convexity parameter over this. So essentially I can consider that the Lipschitz constant of the gradient of that is like the highest eigenvalue of my problem, and the strong convexity of this is like the smallest, so that L square over delta gamma is here the condition number. So I get, introducing the condition number, so it's not gamma delta, it's gamma mu, but it's what I said. I get some equation, and I solve the equation, and I find that the contraction factor is again like square root of the condition number here. Is a function of the square root of the condition number. So it's like 1 over this quantity. And so if you want, if k is large, which is the bad case, it's like 1 over 2 over square root of k, which is essentially the optimal ratio. It's similar, it's a bit better for methods like heavy ball methods or conjugate gradient or things like that, but it's essentially the good ratio. So we end up with this big inequality, which is to be expected. We multiply by theta minus k, because we have something which bounds the same thing, which was 1 over theta, and it's only this at k plus 1, so I can sum. I get a big inequality with theta to the n here, the initial situation here, and this bounds the value at n. Of course, you still have this bad term, so you need to eliminate it, so you do exactly as before, and if you do exactly as before, this will exactly cancel this term, so that's bad. You end up with some control only on one variable here. So because I've been too optimistic, and maybe you shouldn't take this equal to 1, you should take it a bit less than 1, and if you do that, then you keep, this does not cancel completely that term, and you keep part of it. So normally you should take probably time step a bit smaller than what I said, and get a slightly less good rate, but then you get a good control on both variables. So what about the stochastic case? I will not detail the full calculation. The only point is that essentially they are identical with a slight modification. So first, the algorithm is essentially the same here. So this is the optimality. The optimality is the same, but no, it's expressed in terms of the variable y, which is a group of variable yi. And the stochastic algorithm is essentially the same, except that instead of doing this on the global y, you just do it on one, for instance, on in that case here, on one point, yi, which you choose with a probability pi, and you don't do anything for the other variables. So this should be j. Sorry, this should be j. Okay, and then you update x as before, and you do the same calculation, but here they are really the same calculation. So for the yi you have picked, you have this inequality. Of course, for the ones you have not picked, you don't have this inequality because you haven't done anything. And more precisely, you have that if you remove the red terms here. Now, if you consider, if you want, you have that this is equal to that because here you haven't changed this point, and this is 0 because these points are the same. And so if you want to write the same thing on the right hand side, you need to compensate by adding on the left hand side somehow the same terms. So you have a similar inequality, but with it's a bit fictitious. And then since this is with probability pi and this with 1 minus pi, you can end up with some global thing if you take the expectation knowing everything up to k. So you take the expectation here, assuming you know all your sequence up to k, and it's only the expectation with respect to the k plus 1 choice. So it gives you essentially something very similar as before, except that you have these red terms, the red additional terms, which of course when you have one variable with probability 1 disappear, but if you have several variables, then you have something here. And then, okay, then it's just rearranging a bit this. So, okay, you rearrange that, and you get this inequality, which looks very much as before, except here it's a bit less than 1. It's less good than 1. So this is almost this, but still it's a bit less. So there is still a contraction in that term. And this is a bit different as before, but not so much. But don't care about that. So x, of course, is exactly as before. So in the end, you do the same thing. You take xk x bar equal xk plus 1, and y you do some over relaxation, but this essentially most of the time doesn't do anything because these are equal. So it's only for the new variable which has been updated that, or essentially it's for the variable which has been updated as a previous step that you do some over relaxation, which in practice you will see is much larger than when you update everything. So you do some calculation which are not very important, and you get some inequalities where the important thing to observe is that you have this as before. Here again you have this and that, and you don't have one here, but you have factors which are a bit less than at the next step. And then you get complicated stuff which you can hope to control again as before to balance for each step. And you get this lambda I which hasn't been chosen, and you see here that lambda I should be like 1 over pi more or less, if you want this to be balanced by that. So this particular term here which appears here, which involves the differences at the previous step of AI, so this is something which appears only for the variable which has been chosen at the previous step, can be evaluated. Also an expectation, but no, it's the expectation with respect to the previous choice by some quantity where the individual norms. So of course you can do something more general, which was introduced in a paper by Zheng Su and Peter Recherche last year, which is maybe you know what ESO stands for.
Expected separable over approximation. ESO.
Okay.
Very easy.
Very easy. But you can find more general, what I mean is that you can find more general weights for this could be true in some situations, but in this particular situation the simplest is to bound this by the norm of this operator, to take the expectation with respect to all the possible choice of ik, and you get some inequality where you have this bad thing here. So you get this big recursion. I don't, it's not very, I don't want you to follow that in detail. So, but you get again this term. It's really very similar to the previous term. It's just more tedious. You get this and here. This is almost the same except that I haven't fixed lambda I here. You get this big thing and this thing here. So here you see that this you will need to have essentially the factors here comparable to the factors here. So here, essentially, this should be of order 1, or maybe a theta if you want some construction theta. And here, again, you should have this equal to that up to a factor theta. So you need to choose, so theta is called omega no, I'm sorry, but it's the same as before, it's a contraction. If you choose this lambda I like omega over pi, to get the contraction here, this like omega, essentially, so I put 1 over omega in front, so this like omega, and if omega is the contraction here, so it is equal to that, and it is equal to this ratio, so that is this ratio here, and this ratio here. So if you can choose omega like that, lambda I like that, so you can always choose lambda I like that, and pi such that, and lambda I such that this is true, then you get a global contraction. So this you can rewrite like that. And it turns out that this, so that's the nice thing with this strongly convex case, which is not completely true with the partially strongly convex, so 1 over k square acceleration. You get much more complicated formulas, and we couldn't really find the optimal solution. But in that case, you can completely solve this system. And if you solve completely this system, you find that probability is proportional to square root of kappa I, which is, I will comment on this later on, where kappa I is the condition number for each Fi. You get a particular choice of the sigma and tau, which can be done. So tau, of course, as you expect, tau is like 1 over n, because tau is a step on x you do at each step. So you do it very often, so you should do it with a very small step. That's probably the bad thing here. You would probably like to do that less often with a larger step. But if you do that, you get this global contraction rate, which is very good, because, for instance, in the deterministic case, no, not the deterministic case. Wait, if all your factors are equal here, this is like 1 plus square root of k multiplied by n. But at each step, you do only 1 over n iteration if you want with respect to the deterministic case. So if you take the power n of that, it's like 1 minus 2 over square root of k. So it's like exactly the deterministic case, but if you think more about that, it's even better. I mean, it's not always better, but it can be even better, because if all ki are equal to k, it means that all these things have the same Lipschitz constant, but the global Lipschitz constant, depending on how your variables are correlated, could be smaller, could be larger. So it's between, if you want, it's between this L and the square root of n times L, I guess. So if in some cases this rate is even much better than in the deterministic case. So this is a very standard observation when you get this kind of rating. So this idea of taking non-uniform probabilities is quite obvious, and it has appeared particularly in similar work where, interestingly, it's exactly the same thing, more or less, which appears that you have to take it proportional to the square root of your Lipschitz constant or your square root of your condition number. So in these 2 papers, in particular of last year of Nesterov and Stich, and Alan Zhu, Zheng Zhu, and Peter Richterich, and Ivan. So they take also the same kind of proportionality rule to get optimal rates. So I will, so maybe I will finish a bit in advance. I will illustrate this with experiments which have been computed by Matthias here, where G is essentially the total variation for which we almost solved the prox, and with a small additional strong convexity, which is added so that we can make the experiments which are conforming to the theory. And the AI, so it's a synthetic path reconstruction where AI will correspond to different directions of your transform. And he did 2 series of computations. So he did a series of computation with all AI essentially identical, so identical with the same condition number, and another with groups with different sizes, so that you have different condition numbers. And the results, I think, are quite interesting. So, so this is essentially the solution you expect with uniform sampling. This is what would give you for a certain number of iterations. So it's essentially with the same number of iteration, not same number of iteration, because here you will do, let's say, 5 iteration of the deterministic algorithm, and you would do 5n iteration of the probabilistic algorithm to compare. And here you see that with this algorithm and with standard stochastic algorithm, which are not really optimized, you get something where you see a bit the result, but it's very blurry. And with this optimized technique, you improve a lot the result. So this is conversion curves of the objective of the energy with respect to the number of iteration multiplied by n in the stochastic case. And if you do non-uniform sampling, it's even nicer, because you really see here that so the idea here is that you have really sets of directions which are of very different sizes, so you have very different condition number, and you take of course more often the sets which have worse condition numbers according to the rules. And you see that if you really take the optimal probabilities, you get much better curves than if you take uniform probabilities, which is also natural, but the experiment is very nice. Okay, so this could be improved yet with more technical stuff. One thing is that we have a rate 1 over k square in that case, but I'm not too satisfied of how the probabilities need to be chosen. I don't know what you think, you tell me. And so it works, but. And also in practice, you would like to evaluate either not at each step or not exactly this, so that could be interesting to understand what happens in that case. So I will finish here. Thank you.
So, questions? I have 2 questions. One is a personal one, and the second one is more general. So the personal one is, would you recommend us that we should do stochastic or probabilistic algorithms in general? And the second question is, one of the biggest problems in complexity theory is to ask, essentially, does stochastic or probabilistic algorithms helps? In other words, is P equal to B, P, P? Now, in this case here, you show us an already very good algorithm in the deterministic case, for which you tweak and make it stochastic, and it improves it better. But what we don't know is could there be another deterministic algorithm that could be as good as the stochastic one? And the problem here is, how do we actually formulate that question? Because this is sort of over the continuum and not a discrete case.
So that's that's a very good question. So in general, about stochastic versus deterministic, I think stochastic algorithms are really used now in situations where you cannot really do otherwise, like in learning or whatever, when you have a lot of a lot of functions or a lot of sets, or and even sometimes where you cannot read everything, or you don't even know maybe everything or something like that. So in that case, you cannot do otherwise. Well, in the situations where you can choose between deterministic and non-deterministic, there are a few. I think, for instance, Peter Richard has studied that. There are a few situations where it's really apparently better to do stochastic. Like here, for instance, you see that you practically get. It's like coordinate descent. You expect with coordinate descent that you improve. You usually take longer steps. You improve your convergence. Except that in general, with deterministic coordinate descent, it's very hard to prove good rates. While with stochastic, there is this mixing trick which makes it work. Probably in practice, it might be best to do some deterministic with or some shuffling when you do coordinate descent.